the rate law. All right, let's take a look at this particular reaction. So we've got nitrogen dioxide reacting with fluorine gas to form NO2F. The rate law for this reaction would describe how the rate of reaction, so how quickly this reaction occurs, is dependent upon the concentrations of the reactants. And so we know that concentration affects the rate of reaction, but how it affects the rate of reaction can be described by this thing that we call the rate law. So today we're going to try to figure out how you go about coming up with the rate law so that we will know how the concentration of the reactants affects the rate law specifically. So a rate law looks like this. We've got essentially the rate of the reaction, so how quickly the reaction occurs, and generally we're measuring that in moles per liter per second, so how the concentration changes per second, and we could do that by either measuring the decrease in the reactants or the increase in the products. So the rate is going to equal this constant multiplied by the concentration of the reactant raised to a particular exponent. And it could be also the concentration of the other reactant raised to another particular exponent. So we can calculate out what effect this concentration has, so the concentration of NO2 has on changing the rate, or the concentration of F2, what its effect is on the rate of reaction. And it is going to be dependent on these exponents here. So we're going to be essentially solving for what those exponents are. So the K is going to be what's known as the rate constant, and K will change with temperature, but as long as you keep the temperature constant, the K value for any given reaction will be the same. The exponents, in this case we use M and N, but whatever the exponents are, it doesn't matter. But they are essentially the order of reaction, or what amount that particular reactant, so M is referring to NO2, and N is what's referring to F2, how those reactants affect the rate of reaction. And we call them the orders of reaction. If you add those two together, so the orders together, if you sum them up, that's going to be the overall order of the reaction. So the rate law must be determined by experiments. We have to run some trials and we have to say, okay, if I play around with the different concentrations of these reactants, what effect is there on the rate of the reaction itself? And then using that experimental data, I can determine what the rate law is for a given reaction. And once you have it for a reaction, it would be always that rate law for that given reaction. The exponents would be always the same. K, as long as the temperature is the same, would always be the same for that particular reaction. So a couple of things. So if we had our exponent M here, if we do the work and we find out that M is equal to 1, then what that's saying is that if you change the concentration of NO2 and you double it, and the exponent is 1, then whatever you do to the concentration of the reactant, that same thing would happen to the rate of the reaction. So if you double the concentration of the reactant, because M, in this case, if it were 1, doubling the concentration of the reactant would double the rate of the reaction, because it says it's an equation. So if you have one side doubling, then the other side is also going to have to double. And if M is equal to 1, then whatever change you did to the concentration, you'd see a proportional change to the rate itself. However, if M is equal to 2, let's do this. If NO2 is tripled, the rate is tripled. So if you double it, the rate will double. If you triple it, the rate will triple. If M is equal to 2, though, you're seeing an exponential effect on the rate. And so if you had M equaling 2, so the exponent is 2 on the concentration of NO2, then if you doubled the NO2, you wouldn't see a doubling in rate, you'd see a quadrupling in the rate because it's an exponential relationship. If it was tripled, because it is exponential, it would be nonupled, if that's a word. All right, let's try this out. So the experimental data that you'd be getting for determining the rate law for a particular reaction would look kind of like this. You'd run a bunch of different trials, and you would try out different concentrations. So remember, capital M, that is moles per liter, molarity. So you take your NO2 and you try out different concentrations in different trials. And you take your other reactant, if there is another reactant, and you try out different concentrations in different trials as well. And then based on what those concentrations are, you measure the rate of the reaction. And so essentially what we're trying to do is we're saying, okay, if I change something about, let's say, the NO2 reactant, what effect does that have on the rate? But because there's two variables, I have to be careful that I'm seeing which variable it is that's affecting the rate. So I want to see, okay, is the change in NO2, is that going to have an effect on rate? So your trials are going to be set up such that if I change my NO2 from, let's say, one trial that has 1 mole per liter and the other trial that has 2 moles per liter, then for those two trials, I'd want to keep my F2 the same, because if I change two variables at the same time, I don't know which one's causing the effect. So you set it up in a way that one of them changes and the other one doesn't. And so if you look at, let's say, trials 1 and 3, NO2 has not changed, but F2 has. So then we can say, okay, well, using trials 1 and 3, we can see what effect there is on the change in the rate. Using trials 1 and 2, we can see what effect there is on the rate. And then we can determine the rate law for this reaction. So let's go through this the long way first, and then we'll see if we can do it by doing a little bit more thinking and therefore less work. So first off, we've got our rate law equation. So we know the rate is going to be equal to the rate constant K multiplied by each reactant raised to some exponent. And we want to find out what that exponent is. So what we can do is we can pick trials that will eliminate out the other variable. And so we'll pick the trials accordingly so that we can eliminate that other variable. Three variables here. We're gonna essentially use K. We're gonna make sure that it is going to be eliminated because K is going to be constant between the trials, so it eliminates itself. We just have to pick two trials where the other reactant will also be eliminated, and then we're going to solve for the M variable and find out what it is, and then we'll do the same thing for the N variable, the N exponent. So we're going to solve for one exponent at a time, essentially one reactant at a time, or its particular exponent. So we want to use a trial where just that particular reactant is going to be changing, so we can solve for its particular variable, which is in trials 1 and 2. And essentially we're going to take the data from trials 1 and 2 and plug them into the rate law and cancel out the other variables. So if we look at trial 2, we can take the rate, and we can take the concentration of the NO2 and the concentration of the F2. And if we divide the information from one trial by the information from the other trial, we're going to be able to cancel out these variables. Essentially, we're dividing one equation by another equation in order to eliminate variables. So this will quickly get rid of our k's, because k divided by k is going to cancel out. But more importantly is it's going to get rid of our n variables as an exponent, because 1 to the power of n divided by 1 to the power n is also going to cancel out. So very quickly we've gone from having 3 variables in our equation down to 1 variable equation by using trials 1 and 2. Now I put 2 divided by 1 just because nobody likes fractions, and so in this case I have my rate of 2 divided by my rate of 1, or 2 times 10 to the negative 4 divided by 1 times 10 to the negative 4. So I end up with a whole number instead of a fraction, but it would work out just fine if you did it trial 1 divided by trial 2. Either way, we can simplify that, and we can say that 2 times 10 to the 4 divided by 1 times 10 to the 4 is equal to 2. And so they've canceled out, and 2 to the m divided by 1 to the m works out to be 2 to the power of m. And now we can solve for our exponent, and you can do some fancy logarithmic work to solve for your exponent, or you can realize, okay, if 2 is equal to 2 to the m, m must be equal to 1. And the nice thing about these rate laws that we're going to be dealing with is you're going to get very low whole numbers. So you don't have to worry about doing any fancy mathematics. You'll be able to very quickly, once you get to this point, know what the exponent is. So the order of reaction with respect to NO2, which is to say the variable that is the exponent for NO2 in the rate law, is 1, m equals 1. And therefore it's first order with respect to NO2. We can do the same thing for F2. Pick 2 trials in which F2 is changing, but NO2 is not, the concentrations of them. So if we look at trial 3 and trials 1, again, we can see that we're going to be able to cancel out the effect of NO2's change on the rate because they're going to cancel each other out. They both started with an initial concentration of 1 mole per liter. The K's are going to cancel out as well, and very quickly we get to 2 equals 2 to the power of n. So we also know that the exponent for the F2 reactant must also be 1, or that is to say that it is first order with respect to F2 as well. We could sum those two exponents together and we could say the overall order of the reaction, because the NO2's exponent is 1 and the F2's exponent is 1, the overall order is going to be 2. So we can say the reaction is second order overall, or first order with respect to each of the individual reactants. So let's try doing that a little bit faster. So that's a mathematical way where you're using the data from the different trials, you're subbing it into the rate law, you're limiting the variables, and you're solving for the exponent. And that works fine, no problem. But you can also kind of think your way through that as well. So if we pick, we know we've got a variable that we want to eliminate. So if we look at trials 1 and 2, for F2, they're not changing. So any change between trials 1 and 2, if there's a change in the rate, it's not due to F2 because F2 hasn't changed at all. The fluorine hasn't changed at all. So any change in the rate between trials 1 and 2 must be due to the change in the concentration of NO2. So essentially we can say, okay, well, what is that change? We're going from 1 mole per liter to 2 mole per liter. So essentially what we're saying is that the change in the concentration for NO2, what we're doing, we're changing it by, in this case, we're doubling it. We're going from 1 mole per liter to 2 mole per liter. So the change is going to be doubling it. So if we're trying to solve for M as a variable, what effect does doubling the concentration of this NO2 have on the rate? And if we look at the rate, it's going from 1 times 10 to the negative 4 moles per liter per second to 2 times 10 to the negative 4 moles per liter per second. You don't have to think too hard to see what's happening with the rate. The rate is also doubling. So if when you double the concentration of NO2, the rate also doubles, then that tells you what the effect of NO2's changing concentration has on the rate. And in that case, also we can say, okay, well, I can see that it is a linear relationship. Therefore, M must equal 1. We can do the same thing for F2. We can say, okay, let's look at 2 trials where F2 is changing. So let's look at trial 1 and trial 3. F2 is doubling, but NO2 is doing nothing. So any change in the rate would not be due to NO2. It must be completely because of the change in F2, because it's the only thing that's changing. So if we look at the rate between trial 1 and 2, it starts off at 1 times 10 to the negative 4 and goes to 2 times 10 to the negative 4. So the concentration of F2, its effect on the rate, we're going to describe with the exponent n, and we say, okay, well, if we double its concentration of F2, we're doubling it, so I'm putting a 2 in there for that, the effect on the rate, going from 1 times 10 to the negative 4 moles per liter per second to 2 times 10 to the negative moles per liter per second, that is also doubling. So doubling the concentration of F2 doubles the rate of the reaction. Therefore, it must also be a linear relationship. So n must also equal 1. So you can look at the data, and as long as the numbers are relatively easy to work with, you can do it. Otherwise, just pick up a calculator and look at what the changes are. But same idea, much faster way of doing it. So there's our rate law. We can say, okay, we know that the effect of NO2 has a linear effect on the rate, and so its exponent must be 1, m equals 1. And the effect of F2's concentration change also has a linear effect on the rate. It's the n value, the exponent, must also be 1. Now we can solve for k. So since we've solved for 2 of the variables, we can now solve for the third variable k. And essentially what that is just pick any one of the trials, take the rate from the trial, take the concentration of NO2, take the concentration of F2, apply the exponents, and solve for K. So let's take trial 1. We can plug in the data, and so rearrange for K, solve for K, and you should end up with a K value of 1 times 10 to the negative 4. Now, take a look at what we're doing here. So we're saying that the rate, let's clear this up a little bit. So here's our one equation here. I've rearranged for K, so I've taken this side of the reaction, I've divided both sides, so essentially I put it over here. So rate over NO2 to the power of 1 multiplied by F2 to the exponent 1 is equal to K. And then I have plugged in the numbers and say, okay, my rate for the first trial is 1 times 10 to the negative 4 moles per liter per second. The concentration of NO2, and I can put a 1 there, is 1 mole per liter. The concentration of F2 from trial 1 is also 1 mole per liter with an exponent 1 on there. And then I go through and solve, and I will end up with 1 times 10 to the negative 4. Now the units are a little bit trickier to solve for. So we have moles per liter per second on the top, and we have moles per liter and moles per liter on the bottom. So let's just rewrite the units over here. Moles per liter per second is on the top, and on the bottom essentially we have, let's continue this on here, and brackets so we can keep it straight, moles per liter as one of them and moles per liter as the other one. So off the bat we can say, okay, well, one of these moles is going to cancel out with one of those moles. That's okay. One of these liters in the denominator is going to cancel out with one of the liters in the denominator of the denominator. So let's rewrite that a little bit neater now. So we've gotten rid of our moles on top, so I'm just going to put a placeholder of 1 up there. I have seconds on the bottom, this guy right here, and I have moles on the bottom as well. And then I have liters as a denominator in the denominator, which we know is essentially a numerator. So let's actually replace that 1 with the liters. And so I end up with liters per mole second, or second mole, as my units on my K value. So the units for K will change depending on the order of the reaction. This is a second order reaction because we have an exponent of 1 and an exponent of 1. Any second order reaction will have that as the unit, but a first order reaction or a third order reaction would not have the same units because we're going to have different units on the denominator here. So essentially what they're going to work out for is, we did a second order reaction, so it's going to always work out for second order reaction to be liters per mole second. But if you had a third order reaction, you're going to have another dividing by moles per liter. So you're actually going to end up with liters squared over moles squared seconds. Now, first order reactions are just going to be per second, and zero order reaction because you don't have any concentration at all, so they'll just have the same units as rate, and they'll be moles per liter second. Again, you should be able to calculate these based on the rate law itself, but this is what they would work out to be. With our order of reaction, if we were to graph the rate versus the initial concentration, it's not the changing concentration over the course of the reaction, but the initial concentration of the particular reactant we're talking about. So let's say we said NO2 for the last reaction. If we were to graph its initial concentration versus rate, it will tell us, the graph will tell us what order we're dealing with. And that last one, we knew we were dealing with an m equals 1 for NO2, so we said NO2 had the m value of 1. So what it's saying is having a linear effect on rate. So if you were to graph the rate of reaction for that particular reactant, since it is a first order with respect to NO2, you'd end up with a linear line. Let's say we had another reaction though that had some other reactant in there. If its initial concentration, if you were to graph its initial concentration and then change it and measure the rate of reaction as you did that, and you got a slope to it, then you know this must be something other than 1, like 2 or even higher. You just end up with another slope if it was 3 or so, but you'd know it's not a linear relationship. If the changing concentration Actually, let's do another reaction. Let's do Y. So another reactant Y, if changing its concentration, you had a little bit of it or you had a lot of it, and then you measured the rate of reaction and there was absolutely no change in the rate of reaction, well, that must mean it has no effect on the rate of reaction because its concentration doesn't change the rate of reaction. So that would be a zero order reactant.